Hello everyone. Today I will talk about plutonium gallium alloy, a material of great significance in nuclear sciences, and I will be discussing about its property, crystal structure, and many more on this table. So we will start with property table. First one is mechanical property, ductility, elastic modulus, yield strength. The second one is electrical property. Gallium weakens 5F bonding, reducing cohesion. And the third one is electromagnetic and optical properties. Metallic behavior observed in 0.7 to 4.3 electron volt range. Now here is an image of its crystal structure, and its atomic structure is face-centered cubic structure. Electronic configuration of plutonium is Rn5F6 7s2, and its electronic configuration of gallium is Ar3d10 4s2 4p1. Now here you can see the synthesis procedure. Plutonium is obtained in metal or powder form with a specific isotopic composition. Gallium is in high purity form or in liquid form. Plutonium is heated to around 600 degrees Celsius, and gallium is added in small amount and then melted into plutonium. The mixture is stirred for uniform distribution. The molten alloy is then carefully cooled at controlled rate. Here is the phase diagram of plutonium gallium alloy. Here on the x-axis we have atomic percent plutonium, on the y-axis we have temperature in degrees Celsius. The image shows the stable phases of plutonium gallium alloys at different temperature and compositions. This diagram on the x-axis we have gallium at percent, and on the y-axis we have temperature in degrees Celsius. The image shows the focused view of delta phase region with narrow gallium content. Even a small change in gallium content can cause a phase shift. Now we will understand the material configuration. For density, it is lower than alpha phase Pu, and thermal stability, it maintains delta phase structure. Thermal expansion, it is very low compared to alpha phase, and corrosion resistance, it is reduced susceptibility, and Young's modulus, it is more ductile than alpha phase. So now we will see the techniques for studying morphology of plutonium gallium alloys. The first one is FIB SEM, a focused ion beam scanning electron microscopy. It reveals the micro cracks and pores in oxide scales. The second one is Auger electron spectroscopy. It analyzes the chemical composition of oxide layers. The third one is diatometry and calorimetry. It tracks the phase transformation and thermal expansion anomalies. The fourth one is metallographic techniques. X-ray diffraction confirms delta phase stabilization by gallium. Now we will see some key stages of manufacturing. The first one is material preparation. Plutonium is in metal or powder form, and the gallium is in high purity form. The second is safety handling, work in gloves and controlled inert atmosphere. The third one is alloying process, heat plutonium to 600 to 650 degrees Celsius and then add gallium and stir it. The fourth one is cooling and solidification. Carefully cool it at controlled rate. The next one is post-alloying treatment, heat treatment and microstructures analysis. Since we already saw the properties and structures of plutonium gallium alloy, now we will see how nanomaterials are involved to enhance its performance. The first one is gallium nanoparticle. It improves the dispersion and mechanical properties. The second one is plutonium nanoparticles. It study the phase stability and transitions. The third one is nano gallium plutonium interface. It is critical for alloy structure. The fourth one is nanostructured stabilization. It enhances the radiation resistance. The fifth one is carbon nanotubes, potential reinforcement for strength. And the sixth one is quantum dots. It could improve radiation performance. Here are some of the learnings about plutonium gallium alloy. The first one is delta phase stabilization. Gallium stabilizes the ductile FCC delta phase at room temperature. The second one is microstructural dynamics. Gallium segregation occurs in as cast alloys. The third one is aging and radiation effects. Self-irradiation from alpha decay occurs helium bubble formation. The fourth one is oxidation behavior. Oxidation is slow due to high energy barriers for diffusion to subsurface layers. The fifth one is thermal and mechanical properties. Delta phase exhibits near zero thermal expansion. The sixth one is controversies and modeling. Difference in phase diagram are addressed through computation. Thank you.